welcome everybody to Southern California. As director of the Southern California Earthquake Center, my job is to keep earthquakes from happening here. We work, of course, with the USGS and FEMA in this regard. But in case it doesn't work during the meeting, please drop cover and hold on. What I'm going to do is talk a little bit about earthquake system science and some of the progress that we have made and some of the societal impacts it has made over the last 10 years or so. And in constructing this talk, I'm drawing from a number of large collaborations from SCAC, from the Pacific Earthquake Engineering Research Center, the Working Group on California Earthquake Probabilities, and the Collaboratory for the Study of Earthquake Predictability. We are all engaged in what we call earthquake system science, which is trying to build physical representations of fault systems that produce earthquakes that have predictive capability. The fundamental prediction problem that we're after is to provide prospective information about earthquake behaviors that can be useful to society. And of course, there are many earthquake phenomena that we have to worry about in terms of the primary and secondary effects of earthquakes. Some are listed here. But what I want to emphasize is that California has been one of our primary laboratories for developing the science and its applications to the earthquake problem. And of course, we sit here astride the San Andreas fault system. We have high rates of seismicity, and we have, fortunately, many organizations that are helping to try to address the problems of earthquake risk and resilience. So let's look at the risk equation, remind ourselves why Southern California and why California in general has such a high risk. It's because we have a high earthquake hazard. Earthquakes, nature throws a lot at us here in California. We also have many people, very high exposure to those earthquake effects. Our building stock is pretty good, but it's still vulnerable in certain places, many issues we need to address. And of course, as Glenn emphasized, we have to really focus on this issue of resilience, because when the hammer hits, we've got to be able to rebound and reconstruct. So one of my points is that earthquake system science, sort of the top-down approach to earthquake problems, provides key information for all of these activities because it allows us to essentially evaluate the effects of actions we might take to improve our vulnerability and our resilience to earthquakes. There's no better example of that, I think, than what happened this last year. On October 9th, the LA City Council unanimously passed ordinances that mandate retrofitting for certain types of buildings, so ones that, if you live here in Southern California, you worry about, the soft first-story buildings and the non-ductile concrete buildings. And it's remarkable that this happened. We know politically how difficult it is to make these kinds of changes and develop these kinds of regulations, so it's worth asking, how did this happen? And the way it happened was Mayor Garcetti was committed to the problem, and he appointed Lucy Jones to chair a seismic task force for the city of Los Angeles. And they came up with this plan called Resilience by Design, which has plans for strengthening buildings, as I just mentioned, but also improving resilience by fortifying the water supply system and enhancing telecommunications. And this, of course, is just the beginning of what we hope is continuing efforts to improve the resilience of the city of Los Angeles and surrounding areas that are so threatened by earthquakes. Now, in this report, they presented a very strong case, and the way they did that was they used the 2008 shakeout scenario, which was a science-based earthquake scenario, to essentially as the scientific basis for this report. And of course, shakeout was based upon a detailed earthquake simulation that was then packaged with appropriate aftershocks and effects that might occur, a rather detailed simulation. In fact, the earthquake simulation that you see here, which was done by Rob Graves of the USGS in collaboration with SCEC, was the largest and most advanced earthquake simulation we had to date. You know, I think a lot was really learned about this and other potential earthquakes that might happen in Southern California. And, you know, learning from a virtual earthquake is a lot better than learning from the real thing. The other point is that with the appropriate type of leadership, the sort that Lucy Jones and her colleagues exerted in this process, we can use the scientific characterization of hazard and risk to implement effective mitigation options that are well-defined, have well-defined costs and benefits. Now, the shakeout scenario continues to inform not only the science of earthquakes, but also provides a basis for a set of national and now international drills that are occurring. Drop, cover, hold on, teach your neighbor, interact with your community to learn how to deal with these disasters. And remarkably, this last year, over 43 million people worldwide were registered to engage in the shakeout exercises. And this is really a remarkable testament to the developers of Shakeout. Lucy Jones was one of those. To the people who are running this program, Mark Benthian in particular, and his colleagues at SCEC deserve a lot of credit for making this a worldwide exercise. Now, earthquakes are incredibly complicated. They proceed as complex cascades from the natural environment into the built environment. This is sort of a kind of a complicated schematic showing a lot of the interactions that occur before and after the earthquake. Notice sort of the very nonlinear time scale that goes from a century before to a decade after. Earthquakes are extended phenomena. And in fact, the seismic hazard and risk issues are really dynamic prediction problems and requires forecasting models that are both probabilistic to take into account the uncertainties and time dependent because the earthquake systems are changing with time. Now, earthquake system science that has been developed over the last 10 years or so has really contributed to enabling new technologies for us to track these earthquake cascades. And I show these in this upper figure. You can see the red labels and the sort of the time periods over which these systems are appropriate. So for example, we have now new tools for post-event information and to provide the kind of information we need for emergency response. And the USGS has really led this effort. Dave Wald, who is here, has been a major leader in developing the USGS pager system, which gives very rapid assessments of potential damage and casualties. The Shake Map system that provides emergency managers with rapid information about where the large shaking has occurred. And the Did You Feel It website, which allows people to log in their experience with the earthquake. And it turns out that a lot of people who are appropriately calibrated reporting through the system are just about as good as seismometers in terms of us being able to assess the shaking. We also have tremendous strides being made in earthquake early warning. You'll hear about that this morning. Of course, the idea here is that we detect an earthquake as it's happening. We inform people downstream from the seismic waves that they're about to get shaken. Systems are now in place in California, the Shake Alert system that are active, being developed. This is a public-private partnership and one that has great potential for informing our citizens during those moments that the earthquake is happening. I want to talk a little bit more about the long-term seismic hazard modeling because this is really our first defense against earthquakes. If we cannot build a safe environment, we will not be able to withstand earthquakes and bounce back from them. And the process of, is this a pointer? Yeah. The process of seismic hazard analysis involves two major constructions, models. We have to worry about the earthquake rupture process of where the faults are, how they slip, how large the earthquakes they produce might be. We then have to transport that information outward to places that get shaken. We have to be able to predict the ground motions that are caused by these large earthquakes. So we have to know how that ground motion changes as you move away from the earthquake, as it decays. So we have new tools for this. In particular, the Uniform California Earthquake Rupture Forecast, or USERF, has been a major innovation in the last 10 years. This activity has been a collaboration between USGS, SCEC, the California Geological Survey, with major support from the California Earthquake Authority. Thank you, Glenn, for that. Another major activity has been sponsored by the Pacific Earthquake Engineering Research Center, the development of new ground motion prediction equations that allow us to estimate the shaking that might occur at various sites. And these tools are then used to develop seismic hazard maps. This shows the California component of the National Seismic Hazard Map, which employs both USURF-3 and the NGA models developed by Peer. The USURF models have come in, been developed over a period of 10 years. There's USURF-2 in 2007. USURF-3 was released in 2014 as a time-independent model, the time-dependent model in 2015, and a short-term model is about to be published, or will be published hopefully within the next year, an activity led by Ned Field. The Peer NGA project has been a major contributor to our ability to improve seismic hazard maps. And I think it's useful to note that the combination of these efforts provided CEA with the science basis for insurance rate decreases that were rather substantial, about 21% in 2006 and over 12% in 2012. So earthquake system science has helped to reduce the cost of earthquake insurance in California by 1/3. And that helps Glenn and his colleagues at CEA address this critical problem of insurance penetration into society. But this is not enough. PSHA, as it's currently practiced, is based on empirical statistical models. Both USURF and the NGA models are rather empirical. And there's a lot of uncertainties, a lot of variations in the ground motions, for example, that these models just don't properly describe. So we think we can improve on that by building on top of these empirical models, physics-based models, that use the more advanced scientific concepts that we are now beginning to understand and how earthquakes work and how the waves propagate. And so I'm going to mention in this talk the earthquake rupture simulators, ground motion simulators. These are physics-based simulators that allow us to forecast ground motions and therefore calculate the sorts of intensity measures we need to use in our engineering and design. Here's the problem. This shows, this is sort of an old model, but it nicely shows what I want to mention. Namely, this is a plot of ground motion amplitudes. This is peak ground acceleration as a function of distance away from the event, logarithmic scale for distance. And you can see that as you move away from an earthquake, the ground motions decay with distance, as you would expect. And this red line represents a ground motion prediction equation that predicts that decay with distance. You'll notice a couple of things. First of all, there are regions, especially close to earthquakes, where we have very little data. And secondly, there's a lot of scatter about these curve fits to the data, a lot of unexplained variability. And we pay a price for that. This is a seismic hazard curve that shows the annual frequency of exceedance as a function of the ground motion amplitude. In this case, it's 3-second spectral acceleration, long period measure. But the point is that if you increase, for example, the uncertainty in your ground motion estimation in this sort of logarithmic form by 1/3, you can see that you can change the probabilities by orders of magnitude. So it's important that we try to do that, and the way we do that is through large-scale numerical simulation. That requires that we have good descriptions of the seismic source, physical descriptions. We have to have three-dimensional models of the geology because, as you'll see, the earthquake waves are guided by the geologic structures, and a lot of the variability that we see in earthquake shaking is due to those geologic effects. And of course, we have to be able to do these calculations, and they are very heavy-duty calculations. This last year, Southern California Earthquake Center received allocations from the Department of Energy and National Science Foundation for 362 million hours of computer time. So we're using about 1 million hours per day of computer time to do earthquake simulations. This is a plot of computer capability measured in teraflops per second as a function of time going from 2004 up to the present time. And what you are plotted on here are the capabilities of the largest supercomputers in the United States. And those capabilities increase, although not so rapidly lately, according to something called Moore's Law, which you may have heard about. What I'm going to superpose on here are the performance that we've been able to obtain on specific simulations. Those are always going to be less than the ideal performance of computers. But what you'll notice is that the simulations being done through the Southern California Earthquake Center are increasing in terms of the computer performance, and of course that increases due to the complexity and also our ability to know how to use these very large-scale computers. And you can see we're approaching very efficient usage, and you can see that in the future we are going to continue to need the largest supercomputers that we can find. So I'd like to walk you through a few simulations indicated on here, starting back in 2006, the Terra Shake simulations, the Shakeout simulation, M8, and then some more recent simulations that involve new physics that we're putting into the problem. So here's an example. This is a picture of Southern California to get you oriented. We are down here in Long Beach, about here. And what is being plotted here is the ground shaking expected from a magnitude 7.7 earthquake on the San Andreas Fault to the east of here. This particular calculation was done with the empirical ground motion prediction equations that were used in the National Seismic Hazard Map at that time, and you can see the large area of potential shaking. However, when we ran this using a terascale simulation, something called Terra Shake program, we were astounded, actually, to see such differences from the ground motion prediction equations. And in particular, you'll notice that the ground motions in the Los Angeles region are much higher than they would have been, or than would be predicted by the ground motion prediction equations. And this is associated with a coupling between the so-called directivity effect of earthquakes and basin excitation. And I'll show that more in a second. But the basic point was that these early simulations indicated strong 3D focusing of ground motions from strike-slip faults in California, and they quantified the importance of things that are not properly represented within these empirical equations. So here's the Shakeout simulation done in 2008. It mimicked that 2006 simulation. It was chosen, in fact, to have the same effect. You'll notice how the waves get bent from the San Andreas Fault, bent into the Los Angeles area, and you'll notice the extended shaking that occurs in the Los Angeles area. And that, of course, was the shakeout event that's been analyzed so carefully and for which we now know would be a $250 billion event or perhaps more. Many interesting consequences have been drawn from this event. The one I often tell my friends when they ask about this is I said, do you realize that the sewer system will be out for about 6 months or so? And, well, no further comment is necessary. The shakeout event is not the largest event we can imagine. In fact, the entire southern San Andreas Fault is capable of rupturing in a single earthquake. That would be about a magnitude 8 or 8.1 earthquake. We call this a wall-to-wall event. We've simulated that in 2010 using the world's largest supercomputer at the time. And you can see that this area of influence by the shaking is now expanded out to huge proportions. And in fact, if you look at how this event propagates, in this case starting at Parkfield like 1857 did, propagating down the fault, you see that big directivity pulse out in front as that energy is being shoved down the fault. That directivity pulse bleeds energy into seismic waves that excite the sedimentary basins like the San Fernando Valley and the Los Angeles Basin. This rupture is continuing down through San Bernardino. I wouldn't want to live in San Bernardino, actually. But you'll notice, again, the large shaking in the Los Angeles region persisting for long periods of time. Our more recent simulations are focusing on complications that help us better predict the ground motions. One of them is the roughness of the faults that break, that generate lots of high-frequency energy, and also the small-scale heterogeneities in the near surface. And those are represented in the second model below. You'll see how that wave field is much more incoherent because of the scattering from small-scale heterogeneities. By including these effects and also the effects of nonlinear wave propagation, here's a simulation where the near surface has a plastic-like behavior, consistent with real rock behavior that absorbs energy. And what that does in a shakeout type scenario is it reduces the energy that actually comes into LA. We still have a problem, but it reduces the amplitudes of that ground motion down. So we're learning more and more about what individual earthquakes would look like, large earthquakes. And the physics is getting to be pretty good. But of course, that's not enough because we have many faults in California. One single simulation or even a set of scenarios isn't going to capture the hazard that we have from all of the faults in the Southern California system. That white circle is a 200-kilometer radius around downtown Los Angeles, showing you the faults that could generate energy that might be destructive in that region. So what we really have to do is calculate very large ensembles of simulations, and we now have a new platform, the CyberShake platform, that uses clever computational methods to make these simulations extremely efficient. And the way this is done, I have time to go through the details, but just let me point out that input into these calculations is the USURF model, which has the faults and the ruptures, a three-dimensional image of the Earth structure beneath Southern California and over a large region done with high-resolution tomography, sophisticated models of the complexity of the earthquake slip, and out of that comes synthetic seismograms. And not just one or two, but lots of them, enough to where you can probabilistically treat them, you can make hazard curves, you can make hazard maps. In fact, for CyberShake models for the Los Angeles region, there are over 300 million seismograms go into one model. Here's a series of such models. The top one shows the seismic hazard map. This is for 3-second spectral acceleration from a one-dimensional model. The lower three use much more realistic three-dimensional structures. We don't exactly know the three-dimensional structure, and the variations you see in these maps give you an idea of the uncertainties in that structure. But you'll notice how different the three-dimensional models are from the one-dimensional model. Notice the big red stripe along the San Andreas. That's because of the big directivity pulses running up and down the San Andreas fault, causing large ground motions. But in the models below, that stripe gets attenuated because that energy gets scattered out. And unfortunately, gets scattered out into the basins that cause strong seismic shaking in Los Angeles, San Fernando, and so forth. Now, if you compare that with a model that's currently being used in the National Seismic Hazard Map, that's this is the one, this is from 2008, the next generation attenuation model. There's a revised model 2014, but it looks similar. And you can see that there are significant differences between the models we're now using and the models we're computing using these advanced physics methods. So CyberShake has really been a major achievement from our point of view. It's the first complete probabilistic seismic hazard model that's based entirely on these physics simulations. It's leading to a better mapping of the urban seismic hazards, an example of what the USGS calls urban seismic hazard map, and it is now being investigated by engineers for use in, for example, the design and designing the structural integrity of large buildings. I won't have time to talk about the validation problem. It's a critical problem for earthquake science, namely, we're sitting here trying to figure out what's going to happen in the next big earthquake, and we won't really know until it happens. However, we do have smaller earthquakes that occur, and what this graph shows you is seismograms at low frequency from the La Habra earthquake that occurred a couple of years ago. And that earthquake is superposed on that. In red is the synthetic seismograms from the models we use in CyberShake. And you can see almost a wiggle for wiggle comparison. And this event was not used in developing the model, so this is a prospective test of the model. And the model does fairly well at these low frequencies. And we're trying to push this up to higher and higher frequencies. And we think, in fact, that we can, a careful analysis of variance suggests that we can reduce the uncertainties in the GMPEs from values that are typical now, with these sigma values of about 0.6, down to about 0.4. That's about a third reduction in standard deviation, a factor of 2 in variance. And that can have a huge impact on the design of critical facilities, such as nuclear power plants and energy transportation systems. And we're working with PG&E and with the USGS in a major new project in Central California to test out these ideas and try and demonstrate, validate the fact that we can actually reduce these uncertainties. The last topic I want to talk about is to come back to this issue of earthquake forecasting and talk about the problem of operational earthquake forecasting. That is, trying to forecast how seismic hazards are changing with time. We can't predict earthquakes with any skill in terms of short-term timing of earthquakes, but we do know that the seismic hazard is changing in time, on timescales of hours to days to weeks, because earthquake activity within the fault system is rearranging the stresses in that fault system and changing the hazard. And so what can we do about that? Well, of course, our models are typically long-term models. So this is the National Seismic Hazard Map, and it references to this anticipation time scale. It's good for trying to anticipate earthquakes on the time scales of centuries or decades. It's really a long-term model. USERV-2 is a time-dependent model, but still a long-term model. However, we do have new types of models based on short-term statistical analysis of seismicity. You know, when an earthquake happens, of course, you have aftershocks, so that's an indication that earthquakes themselves change the probability of having earthquakes, and we know that earthquakes cluster. So those models can be used to develop models such as this one, the so-called short-term earthquake probability model that has been deployed in the past in California. This shows the increase in seismic hazard associated with the aftershocks of the Chino Hills earthquake in 2008. The USERV, let me point out, however, there is a gap, something we call the middle term gap, between these long-term models and short-term models. USERV-3, the latest iterate, has begun to address that by combining the short-term and long-term models in a self-consistent way. But we still have a lot of work to do. We'll hear some aspects of this during the current meeting, but I want to close by just talking about a new type of physics-based simulation, and that's using earthquake rupture simulators, where we actually model the fault system, the stresses within the fault system, the stress transfer within the fault system, the nucleation processes within the fault system. And I would venture to say that over the next 10 years or so, these are going to become very important tools for earthquake forecasting. They do a much better job of tying together the long term and the short term, and also they allow us to think about what happens over the very long term. And I want to emphasize this. You know, here's a map of California. There's the San Andreas Fault. The Pacific Plate is moving to the northwest at about 5 meters per 1,000 years. 5 meters per 100 years. So what that means is about every 100 years there have to be earthquakes that can take up that 5 meters of slip. Well, earthquakes with that scale of slip do occur on the San Andreas Fault. For example, there was the 1906 San Francisco earthquake, average displacement of about 4 or 5 meters. The 1857 Fort Tejon earthquake, longer ago, and then there were earthquakes that we don't know as much about in 1812 on the southernmost San Andreas, and before the historical record, but from what we can see from paleoseismology, there was an earthquake in about 1680 or 90, maybe as late as 1700. But the point is the time since these earthquakes, if you calculate the so-called open interval, is long. And it's unexpectedly long. California has been too quiet seismically. The springs of the San Andreas system have been wound very, very tight. And the southern San Andreas Fault in particular looks like it's locked, loaded, and ready to roll. Now, this is one of my last slides. I just want to show over here on the left, this is a diagram that shows the open interval versus the average time between earthquakes as determined from geological probing of our faults. And these are various sites along the San Andreas, but you'll notice that these points with time will rise up as the open interval increases if there's no earthquake. And notice how the points are already into zones the open intervals are larger than the typical recurrence times. And we don't really understand that. In fact, our models don't predict that properly. But if you look at the simulator models, they show something very interesting. They show what we call seismic supercycles. This is a catalog, 2 catalogs actually, from 2 different simulators that show variability on a time scale of about 200 years that is plus or minus 50% in the seismic moment release. So one possibility is that we're at the bottom of one of these quiescent periods, and so we're sort of in the trough of one of these supercycles, and that's why we haven't had earthquakes in a while. We don't know that supercycles are real. It's obviously an important research problem, but it does have import in the sense that if this is true, if the faults are really synchronized so that we don't just get earthquakes happening randomly, but we get earthquakes happening essentially in large seismic storms, multiple events, then we have to really worry about how to deal with that enhanced threat. So I'll just put my conclusions up here, and thank you for the opportunity to speak.